Okay, in the previous class we have discussed the sampling of discrete time Fourier transform. So what we have discussed there is that we have taken the Fourier transform of a sequence xn and then we have sampled it. We have sampled the spectrum of xn between 0 to 2 pi, and we have taken n equidistant samples between 0 to 2 pi. So we got its samples as x of 2 pi k by n. Okay, and then we have seen that how you can reconstruct the original sequence x of n from its samples. In fact, what we can recover is a periodic sequence xpn, which is given by this equation. Okay, so this equation gives you an reconstruction formula from which you can generate a periodic sequence xpn from the samples of Fourier transform. Okay, and we have also seen that if your n is greater or equal to the length of the signal, that means the number of samples that you take, if it is greater than the length of the input sequence, in that case your xn will be same as xpn between 0 to n minus 1, otherwise it is 0. Okay, so in that case you can simply recover xn from xpn by just taking its first n samples. Okay, and if n is less than l, in that case you have aliasing in the time domain. Okay, this is what we have discussed in the previous class. Now we will see that how you can directly obtain x omega from its samples, that is x of 2 pi k by n. Okay, means you have a sequence xn, you have taken its Fourier transform dtft, it becomes x omega, then we have taken its samples, it becomes discrete Fourier transform x2 pi k by n. From x2 pi k by n we have a, when you reconstruct it you get xpn, and from xpn then you generate xn by just taking the n samples of xpn. Okay, now we will show how you can get x omega back from the samples of x omega directly. Okay, so for that we use the same equations. Now assuming that n is greater or equal to the length of the sequence, your xpn and xn both are same. Okay, so we already have this equation how can you can reconstruct xn from the samples of x omega, and that is 1 by n summation of x 2 pi k by n e raised to power j 2 pi k n by n, where k is from 0 to n minus 1. Okay, if n is greater or equal to l, your xpn and xn they are same, so in place of xpm I am directly using xn. Okay, so this is how you recover the original sequence xn from its samples. Now how to get the original spectrum from the sample spectrum? Okay, so you can simply use the equation of Fourier transform. xn, which is equal to summation of x of n e raised to power minus j omega n from 0 to n minus 1. Okay, in fact this summation is from n is equal to minus 2 plus infinity, but since the sequence is having only L samples, we assume that xn is equal to 0 for n less than 0, okay, and also 0 for n greater than L. It means your sequence is limited between 0 to L minus 1. So in that case, in the Fourier transform, the summation will go only from 0 to n minus 1. Okay. So now this can be written as, in place of xn, I can use this equation, which is the reconstruction formula. Okay. So I can write it as summation of n from 0 to n minus 1. In place of xn, I can write 1 by n summation k from 0 to n minus 1 x 2 pi k by n e raised to power j 2 pi k n by n multiplied with e raised to power minus j omega n. Okay, and just changing this order of summation here, I can write this equation as x omega is equal to, I first write the summation of k from 0 to n minus 1 x 2 pi k by n, this I have taken, and then multiplied with rest of the factors 1 by n summation of n from 0 to n minus 1. If you combine these two factors, you will see that e raised to power minus j omega n or minus jn can be taken as common, minus jn. What you get inside from this factor, I have taken jn common, minus also there, then omega will be left, minus from this factor you will get 2 pi k by n. Okay, this is the equation for the reconstruction of x omega from the samples of x omega directly. Okay, now we will focus on this part, and you will see that this gives you nothing but a interpolation function. Like we have done in the sampling in the continuous in your time domain, there was an interpolation function. Okay, when you pass the samples through a low pass filter, so the ideal low pass filter, its impulse response was the sinc function. The same kind of thing we are going to get here. So I will discuss this function now. So you have this equation finally, x omega is equal to, it was summation of k from 0 to n minus 1 x 2 pi k by n, then 1 by n summation of n from 0 to n minus 1 e raised to power minus j omega minus 2 pi k by n into n. Okay, if you look to this part, you will see this is nothing but the Fourier transform of a function which is shifted in frequency by 2 pi k by n. And what is that function? If I take a sequence xn is equal to 1 between 0 to n minus 1, otherwise 0. Okay, and if you find its Fourier transform dtft, it is summation of n from 0 to n minus 1 x of n e raised to power minus j omega n, and since x of n is unity, from 0 to n minus 1, it will simply become e raised to power minus j omega n. Okay, x omega. And if I put here omega minus 2 pi k by n, it means if I shift this spectrum in frequency by 2 pi k by n, what I am going to get here is minus j omega minus 2 pi k by n into n. Okay, so this and this are same except this 1 by n factor. It means this function is nothing but the Fourier transform of a signal in which all the samples are 1 between 0 to n minus 1, otherwise it is 0. Okay, and this function, suppose I denote it with interpolation function with pw, p omega. So p omega is my 1 by n. Okay, n from 0 to n minus 1 e raised to power minus j omega n. And this function is shifted in frequency by 2 pi by k, you will get this equation. In place of omega, just I have done here. If you write omega minus 2 pi k by n, you will get this function. So this is the interpolation function. So the shifted versions of this function are basically used in this equation. Okay. So if you calculate it, it will become 1 by n. And this, if you open this series, this is a geometric progression with the common ratio of e raised to power minus j omega, isn't it? If I write it, it will be 1 by n. When n is 0, it is 1. Then e raised to power minus j omega. Then e raised to power minus j 2 omega minus j 3 omega, and so on up to e raised to power minus j n minus 1 omega. So this is a geometric progression series, GP series. The sum of n terms of a GP series is nothing but 1 minus r raised to power n upon 1 minus r. This is for GP, geometric progression. Okay, where r is your common ratio. So in this case, my common ratio is what? E raised to power minus j omega. Okay, so it is e raised to power minus j omega raised to power n. This is capital N. So it is r raised to power n upon 1 minus e raised to power minus j omega, that is r. So you can simplify it. I can take it as 1 by n. From this term, if I take e raised to power minus j omega n by 2 as common factor, you will get here e raised to power j omega n by 2 minus e raised to power minus j omega n by 2. Okay. Similar in the denominator, if you take e raised to power minus j omega by 2 as common, you will get e raised to power j omega by 2 minus e raised to power minus j omega by 2. Okay, and that will become 1 by n e raised to power. Now if you take e raised to power minus j omega by 2 in the numerator, it will become e raised to power j omega by 2. Okay, and between these two factors, you can take minus j omega by 2 as common. What you will get inside is n minus 1. Okay, and for these two functions, for these two, if I divide it with 2j, multiply with 2j. Similarly, divide this with 2j, multiply with 2j. So by 2j, it will become sine function. This is also become sine, and this 2j and this 2j will get cancelled. So it will become sine of n omega by 2 divided by sine of omega by 2. Okay, so this is my interpolation function, right? So using this interpolation function, I can express this equation of x omega like this equation can be written as x omega is equal to summation of k from 0 to n minus 1 x 2 pi k by n, and 1 by n into this is p omega, and here what is omega minus 2 pi k by n. It means it is nothing but multiplied with p omega minus 2 pi k by n. Okay, this is the ideal reconstruction formula for reconstructing the original spectrum from its samples. Okay, and if you see to this equation, now see, if you interpret this equation, x omega is equal to summation of k from 0 to n minus 1 x 2 pi k by n. Okay, and what is my p omega? P omega we have calculated, it is sine of n omega by 2 divided by n sine omega by 2 into e to the power minus j omega by 2 into n minus 1. So this is a complex quantity. It will have magnitude as well as phase plot. If you plot its magnitude response only, okay, if you plot the magnitude response, that is mod of p omega. Anyhow, since it is the Fourier transform of a discrete signal, it is going to be periodic with a period of 2 pi. So we have to plot only between 0 to 2 pi or between minus pi to pi. It will repeat beyond this. Okay. And this factor e raised to power minus j omega by 2, when you see the magnitude of this, it will be simply sine of n omega by 2 upon sine of omega by 2n mod of this. The magnitude of this will become 1. It basically introduces a phase shift. This part, this will give the phase response. This part will give you the magnitude response. Now when you plot it, this interpolation function, so for n is equal to 0, sorry, for omega is equal to 0, what will be the magnitude? It will be sine 0 by 0 form. So we have to use a L'Hospital rule here. So in order to find p at 0, you will take the derivative, that is cos of n omega by 2 into n by 2 divided by n cos of omega by 2, that is derivative of sine omega by 2, multiplied with derivative of omega by 2. So derivative of omega by 2 is 1 by 2. So it will become, so this, and then when you put omega is equal to 0, so this cos will become 1, cos will become 1, n by 2 here and n by 2 here cancel, we will get 1. So at omega is equal to 0, this function has a value of unity. Okay, and this will take the form of a sinc function. So it will have 0 crossing points. Now see, as you increase omega from 0, the function will decrease then increase, and when you reach at omega is equal to 2 pi, again at p is equal to 2 pi. So sine of, when omega is 2 pi, it is pi n, and here when omega is equal to 2 pi, in this it is sine of pi. So sine of pi n upon sine of pi n, it is again 0 by 0. You again apply the L'Hospital rule at 2 pi, its value will be again 1. It will repeat basically after 2 pi. Okay, so in between, the function will take a shape like this. If you plot it, it will be something like this between 0 to 2 pi. Okay, and where will be the 0 crossing points? These points, when your numerator will be 0. It means these points will come when your sine of n omega by 2 will be equal to 0, or you can say when n omega by 2 is a multiple of pi, k pi. or when your omega is equal to 2 pi by n k. Okay, so at 2 pi by n, in case 1 first, at 2 pi by n it will be 0, then when n is 2, at 4 pi by n it is again 0, and so on. Okay, suppose if your n is 5, it means you are taking the 5 samples in the Fourier domain. So this point will be 2 pi by 5. Okay, this is 2 pi by 5. The second zero crossing point will be 4 pi by 5. Then next will be 6 pi by 5. Then 8 pi by 5. Then at 10 pi by 5, that is 2 pi, you will again get 1. Okay, or you can also plot it from minus pi to pi. In case of minus pi to pi, you will get like this. So 0, then this is 2 pi by 5, this is 4 pi by 5, this is minus 2 pi by 5, this is minus 4 pi by 5, and so on. Okay, now this is my interpolation function. Okay, so how you reconstruct the spectrum using this interpolation function? What we do is x omega is equal to this series. If I open it, for k is equal to 0, you are getting x of 0 multiplied with p of omega. Then x1, in k is 1, you will get x of 2 pi by n multiplied with p omega minus 2 pi by n, and so on. It means you have n samples. So the first sample x0 is multiplied with this interpolation function as it is. x2 pi by 5, that is the next sample, is multiplied with a shifted version of this interpolation function. It will be shifted by 2 pi by n to the right, and then multiplied with x of 2 pi by n, the sample at that frequency, and so on. So when you add all these shifted and scaled interpolation functions together, what we are going to get is nothing but the original spectrum. Okay, and you see that you can simply verify that if you sample this function at just omega is equal to 2 pi k by n, what do you get? At omega is equal to 2 pi k by n, this function will always be 1. Okay, see, suppose x0, you take x0, the sample at 0. Okay, that will be in this series, it will be p of 0 into x of 0. So x of 0 into p of 0, and p of 0, it is 1, so it is same as x0. If you find the next sample at 2 pi by n, okay, you will get in this series x of 2 pi by n multiplied with p of, now this omega will be 2 pi by n minus 2 pi n. Okay, or what you can say, I can just say like this, that if this is p omega, when you shift, this is, suppose for n is equal to 5, it was 2 pi by 5, it was 4 pi by 5. So when you generate 2 omega minus 2 pi by 5, you shift this spectrum by 2 pi 5 to the right, so what you get is this like spectrum like this. Okay, this is the first shifted version of interpolation function. Next will be shifted by 4 pi by 5. So next pulse you will get like from here. something like this. Okay, this is original spectrum p omega. This one is p of omega minus 2 pi by 5. This is p of omega minus 4 pi by 5. So as a result, when you sample it at 0, then at 2 pi by 5, only one of these pulses will have the non-zero value, and that will be 1. Rest will be automatically zeros. Okay, so as a result, when you sample x omega at the discrete frequencies, you are getting the same samples as that of the original signal, because at that frequencies these interpolation functions are simply unity, and at all other frequencies they are passing through the zero crossing point. Okay, at if you see at 2 pi by 5, this is 1. This function at this point will be crossing through 0. This function with red will be also crossing through 0. If you take any next pulse, that will be also crossing through 0. It means their contribution is not present there. Okay, at these frequencies. But if you take any other frequency, all these interpolation functions, they will play a role, and when you finally add them together, multiply with the sample, add them together, what you are going to get is the original spectrum x omega. Okay, this is how you recover the original spectrum x omega from its samples. Okay, so we will just take one example. Suppose, so before that, now we will define formally your DFT and IDFT. So DFT, which is the sampling of discrete time Fourier transform. So you have x omega. So you have an input sequence xn. You have computed its dt ft. You got x omega, and assuming that this sequence has a finite length of n samples between 0 to n minus 1. When you take its DTFT, we get its discrete time Fourier transform, and then we have sampled it at a frequencies of multiple of 2 pi by n. We got x2 pi k by n. Okay, these samples, they are basically called as DFT. Okay, so for DFT, we have an equation x2 pi k by n is equal to summation of xn e raised to power minus j 2 pi k n by n, where n is from 0 to n minus 1. Okay, the summation of n from 0 to n minus 1 I have just taken because the signal input is of finite length n samples. Beyond that, everything will be 0 automatically. Okay, so many times we write simply xk in place of x2 pi k by n. We simply write the sample number, that is xk. K may be, k is between 0 to n minus 1. So you take n samples here. So xk is equal to summation of xn e raised to power minus j 2 pi k n by n from 0 to n minus 1, which is equated to xk. This is called as discrete Fourier transform. Okay, so when k is equal to 0, you're getting the first sample, k is equal to 1, you're getting the second sample, and so on. So we're basically getting the samples of the Fourier transform. And then we have a equation to reconstruct xn from xk, that is your IDFT, and that we have already discussed. It is 1 by n summation of k from 0 to n minus 1 xk. Then in place of x2 pi k by n, I am just writing xk here, e raised to power j 2 pi k n by n. So this is the reconstruction equation, which is called as inverse discrete Fourier transform, IDFT. where n is between 0 to n minus 1. Okay, so this is the equation of dft, this is the equation of idft. So using this equation of dft, you can convert a discrete time sequence directly into samples of its Fourier transform. And using this idft equation, you can convert the samples of the dft into the original discrete time sequence. Okay, so let us take one example on this. Suppose we have a finite duration sequence xn, which is 1 between 0 to, let us suppose, l minus 1. Okay, otherwise 0. So you have l samples. You have to see how you can find the Fourier DFT and how you can find IDFT from this. To find the DFT of this signal, you can first find its Fourier transform and then you can sample it at omega is equal to 2 pi k by n. So if you find the Fourier transform of this signal, your n will be from 0 to l minus 1 xn e raised to power minus j omega n. Okay, so it is n from 0 to l minus 1. Now xn is 1, it is simply raised to power minus j omega n. It is again the same GP series, so we will get sum of L terms, that is 1 minus, it is again 1 minus r raised to power n upon 1 minus r, and for this case your common ratio is e raised to power minus j omega. So 1 minus e raised to power minus j omega n upon 1 minus e raised to power minus j omega. Okay, again you can write in terms of sine function. So you can write here as it is minus j omega n by 2, you can take common, it will become e raised to power j omega n by 2 minus e raised to power minus j omega n by 2. Denominator you can take e raised to power minus j omega by 2 as common, it will be e raised to power j omega by 2 minus e raised to power minus j omega by 2. Okay, so you can multiply it and divide with 2j, divide with 2j, multiply with 2j. So this will become sine function, this will become sine. So you'll get sine of omega n by 2 upon sine of omega by 2 into e raised to power minus j omega. From these two factors, j omega by 2 is common. You will get L minus, sorry, I have taken n, it is L otherwise. Okay, otherwise you can take it as L, and here also no issue. N samples. Okay. So j, this will be minus omega by 2 common and minus 1. Okay, so this is the DFT, so no DTFT of this sequence, discrete time Fourier transform. Okay, if you want to find its DFT, what you have to simply do, you have to replace omega with 2 pi k by n. Okay, assuming that you are taking n samples, and this n in this case is just equal to the length of the sample. Okay, so its DFT xk will be simply equal to sine of, now omega will be become 2 pi k by n into n by 2 divided by sine of 2 pi k by n into 2. Okay, and similarly along with the phase factor, you will get e raised to power minus j omega is 2 pi k by n 2 into n minus 1. Okay, so this n and n will get cancelled, 2 will get cancelled, you will get sine of k pi divided by sine of This 2 and 2 will get cancelled. You will get sine of pi k by n, okay, into e raised to power minus j. This 2 will get cancelled. J k pi by n into n minus 1. Okay, this is DFT. Okay, now see, if you plot it, what you will get, suppose I plot the magnitude response of this x omega. Okay, so in the magnitude part I will get only this part. This is the phase part. Okay, if you plot it, mod of x omega, again between 0 to 2 pi only, because beyond that it will be same. Okay, so at 0 you find its value. What will be at 0? Again you have to use L'Hospital root to become cos of omega n by 2 into n by 2 divided by cos of omega by 2 into 1 by 2. So when omega is equal to 0, it will become n. 1 by 2 and 1 by 2 will get cancelled, it will become n. Okay, so at 0 it will start from n, and at 2 pi it will again become n. So in between you have a sinc functions, but when you take the magnitude response, whatever you have the negative values, they will become positive values. Okay, like suppose if I simply plot this without the magnitude, it will become like this maybe. Okay, between 0 to 2 pi you have some zero crossing points depending upon what is n, but when you take this magnitude response, you are getting only the positive values, so it will become like this. Okay, in the magnitude response. Now we take one special case. Suppose you have n is equal to, let us suppose we have an 8-point sequence. Okay, it means 0 to 7, all the samples are 1, and in the Fourier domain we are taking its 8 samples only. Okay, n is equal to 8. We are computing at 8-point DFT. This is what is called as n-point DFT if you take n samples in the frequency domain. If you take 8-point DFT, so here we are sampling at 0, then at 2 pi by 8, then 4 pi by 8, isn't it? Then 6 pi by 8, then 8 pi by 8, then 10 pi by 8, then 12 pi by 8, 14 pi by 8. You are taking 8 samples. 1, 2, 3, 4, 5, 6, 7, 8. Next will be 16 pi by 8, that is 2 pi. Okay, so at 0 its value will be n, that is in this case it will be 8. Then at 2 pi by 8, when you sample it at 2 pi by 8, okay, so when omega is 2 pi by 8, what you will get? If this function, if n is 8, it is sine of omega by 2n, and n is 8 upon sine of omega by 2. So it is basically sine of 4 omega upon sine of omega by 2 for n is equal to 8. So where are the zero crossing points? When 4 omega will be multiple of pi, isn't it? Because sine pi k is 0. So which means omega is pi by, omega is pi k by 4. So when k is 1, it is pi by 4. So it is pi by 4. When k is 2, it is 2 pi by 4, that is pi by 2. This is pi by 2, and then so on. It means again you are getting 8 samples. So first sample at 0, then next sample at 2 pi by 8, it will be 0. Then again 4 pi by 8, it will be 0. Then 6 pi by 8 and so on. All will be zeros. Okay. What it means is that you have taken a sequence. I have taken a sequence, input sequence like this, xn, which was 1 for 0 to 7, otherwise 0. So at 0 it is 1, 1 it is 1, 2, 3, 4, 6 and 7. Sorry, 5. I have taken its Fourier transform x omega and I have plotted it between 0 to 2 pi. It is periodic. Okay. So you have got spectrum like this, magnitude response. It was 8 at omega is equal to 0. Then at omega is equal to 2 pi, it will again become 8. In between you have like this. Okay, this is the magnitude response. So what are these frequencies? This is 0 and this is 2 pi. And these points, which are the zero crossing points, it is nothing but 2 pi by n, 2 pi by 8, and then this is 4 pi by 8 and so on. Okay. Now when you find its DFT, 8-point DFT, if you find the 8-point DFT of this sequence, what it means, you are simply sampling its Fourier transform. You are taking 8 samples between 0 to 2 pi. It means first sample you will take at 0, that is 8. The next sample you take at as 2 pi by n, 2 pi by 8 where it is 0. Then 4 pi by 8, it is again 0. Then next is 6 pi by 8, again 0. So all the samples will become basically 0 except here the first sample, that is at omega is equal to 0. It means it's the DFT xk, you can say it is equal to 8 between 0 to 7, otherwise it is 0. So the DFT of this has a single value xk. If you plot xk at k is equal to 0, its value is 8. Rest all the samples, they are zeros. This is the DFT of this. Okay. Now I can recover this original sequence xn from its samples, that is xk, using IDFT. Okay, and that you have to prove. Now this is a question for you, that for this signal I have already computed what is DFT. Okay, I have taken its Fourier transform, I have plotted it, then I have taken its samples, and I have taken the number of samples equal to the length of sequence, that is 8-point DFT, and I have seen that only one sample at k is equal to 0 is non-zero, rest all are zeros. Sorry, this I have written mistakenly here. This is xk is equal to 8 for k is equal to 0, otherwise it is 0. Okay, now you have to find the IDFT of xk. Okay, this is xk, which is the DFT of the sequence. You have to find its IDFT and you have to verify that the IDFT of xk, that is x of n, it is nothing but this sequence, that is 0 1 between 0 to 7. Anyways, its IDFT should give you exactly the same sequence. Okay, so this you have to verify. So this is what is DFT and IDFT. Many times what we do, suppose we have, like this is a sequence which is a 8-point sequence, but the minimum number of samples in DFT, that must be 8, because n is always greater or equal to the length of sequence. It means I can take 8-point DFT, I can also take it 16-point DFT, I can take 20-point DFT, whatever I want, but I cannot take it 6-point DFT. Okay, and you will see one more thing here, that in this case this was the spectrum of this signal, and when I have taken its 8-point DFT, I am just getting one non-zero sample, that at n is equal to 0. All the samples that you are taking in the frequency domain, they are zeros. All the rest of the 7 samples, they are zeros. It means in the frequency domain you have just one sample, and still you will see, if you solve this question, you will see that you are able to recover this sequence from a single sample only. Okay, but if you take its, this is for n is equal to 8 samples, but if I take, suppose n is equal to 100 samples, what it means, between 0 to 2 pi I am taking 100 samples in the frequency domain, so this sample will become closed. I may get some sample at zeros, I may not get some sample at zeros, but between 0 to 2 pi you are taking 100 samples. From those 100 samples you can again recover the same sequence xn. Means for n which is greater than L, you can always recover x of n from its samples, but the minimum number of samples in the frequency must be equal to the length of the signal. Okay, so this is what is called as, something we call it zero padding. Okay, zero padding means if your sequence has only 6 samples, suppose I take a sequence which is equal to 1 2 3 4 5 6, and if the question is that find 8-point DFT of this sequence. Okay, the length of the signal is 6, L is 6, I can find its 6-point DFT, no doubt. But if I am supposed to find its 8-point DFT, so what we have to do in that case, you have to pad 2 zeros after this sequence so that the length becomes 8, and then you can find its 8-point DFT. Okay, this is called zero padding. So zero padding does not give any additional information, but what you can say that the spectrum looks better. Okay, because we are getting more close and close samples, so the spectrum of the signal in the discrete Fourier domain, DFT domain, that gives a better display. Otherwise you can compute 6-point DFT and you can recover this original signal from 6-point DFT or 6 samples only. Okay, so this is what is DFT and IDFT.